In the last few videos, we have reviewed the Lagrangian formalism in the non-relativistic context, using as main example the free massive point particle in 3 dimensions. We have shown that this action, which is just the integral of time of a Lagrangian, which is simply given by a half of the mass x dot I is invariant under constant space translations, also under infinitesimal rotations, and also under transformations in which you shift the time by a constant. Okay, I'm calling alpha all these parameters, but they are different. And via the first Netter theorem, whose proof we have also reviewed, we have shown that under this invariance is associated to the conservation of the linear momentum. This is associated to the conservation of the angular momentum, and this is associated to the conservation of the energy. We haven't proven, but I am going to leave this as an exercise, that this action is also invariant under the so-called Galilean boosts, which are transformations of this form. Relating the coordinates in two systems that move at relative speed vi. Okay, infinitesimally, they take the form delta xi equal to vi t. You're going to see that the Lagrangian is only invariant up to a total derivative, and the action is only invariant up to a total derivative, but then you can apply the first Netter theorem, as we have shown, and find conserved quantities. Anyway, the upshot is that this action is invariant under the full Galilean group of transformations. Now, in the relativistic case, we are after an action to describe the motion of a free particle, first a free massive particle, because in the relativistic case we can consider also the motion of massless particles. And before we read this action, we could review the conditions that we ask this action to fulfill. So, first of all, it is going to be a functional of the worldlines of the particles. This is the thing that we want to determine. The questions of motion of the particle, the ones that we wrote for the law of inertia, the relativistic generalization of the law of inertia, was written in terms of these worldlines. But clearly, we do not want the results to depend on the particular parameter lambda that we use. So if we go from lambda to some lambda prime, which would be a function of lambda, so we perform some reparameterization, we want the action to have the same form. The second condition is that we want the action, so this functional of the x mu's, to be Poincare invariant. Okay, this is analogous to the non-relativistic action being Galilean invariant, and is a consequence of applying the principle of special relativity. If the action is Poincare invariant, the equations of motion will also be Poincare invariant in their form. Okay. So this is something that we want, and just as in this case there were conserved quantities associated to these symmetries, there will also be conserved quantities associated to all the 10 independent transformations that we can perform, and all the 10 independent Poincare transformations that we can perform if we find this action and it is invariant. finally, this action has to have the right Newtonian limit. So for small velocities, it has to reduce to this action that we have written above, up to maybe a total derivative. Now, these conditions, particularly this last property, should remind you a property of the proper time, or the integral that gives the proper time. Remind you what it is. It is an integral over the parameter lambda, the square root of dx mu d lambda dx nu d lambda. Okay, we saw that in the velocity is much smaller than c limit, this could be written like this: 1 minus 1/2 mv squared. This is a total derivative, and we have learned that this total derivative doesn't change the dynamics. So up to a global sign that we still have to choose, clearly this action has the right Newtonian limit. Furthermore, this is manifestly Poincare invariant. This is why the proper time is Poincare invariant. It is a functional of the x mu's of lambda. So for each set of functions x mu of lambda, this gives us a certain number. So it satisfies all the properties. The only thing that remains to be done is to set the normalization. Okay, this m really I have invented because it is not here now. You only get 1/2 of mv squared. So clearly we need an m here. On the other hand, this sign I didn't invent. We did get this minus sign. So if you want this to be a plus, okay, because you want this by convention, the action to contain plus the kinetic energy, then you need a minus here. And if you want all these to have dimensions of action, then it is not difficult to see that you also need speed of light here. What else can you write there that has the dimensions of the speed of light? Okay, here, this lambda has dimensions of length, and the same is true for the x mu's. So this is dimensionless, this has dimensions of length, and this has dimensions of action. And in the end, this is going to be the action for the particle that we were searching. Okay, once we have the action, we want to derive the equations of motion and see if they coincide with the equations of motion that somehow we postulated for a free particle. That was basically the special relativistic generalization of the law of inertia a few videos ago. So now let us derive the equations of motion and see if they coincide with the equations that we postulated when we generalized the principle of inertia a few videos ago. So the main use of having an action is precisely finding the equations of motion through the principle of least action. Okay, so it doesn't hurt to formulate it in this context. Again, we have worldlines, okay, and we have an initial point, which is an event, a point in space-time, which is an event of coordinates x mu 0, and a final point with coordinates x mu 1, and we consider trajectories, worldlines that join them. Consider all of them, and we compute s of x for all of them, or s of x mu. The principle of least action tells us that the worldline that will be physically realized by the system is the one that extremizes the action, that minimizes it, in fact. And this means that will be the one satisfying these equations. Now, these equations, we know that they are the Euler-Lagrange equations in the non-relativistic case, but it is clear that if we do just the same operations and now we replace time by the evolution parameter lambda here, these Euler-Lagrange equations take the form partial L with respect to x mu minus dd lambda partial L partial x dot mu equal to 0. So this will be the Euler-Lagrange equations. Now we only need to know the Lagrangian, but we can read it because we know that the action here in this context is the evolution parameter instead of t is lambda. This is the lambda, and here we will have L of the x mu's, the x dot mu's, and maybe of lambda. As a matter of fact, the Lagrangian that we have written there does not depend explicitly on the x mu's and does not depend explicitly on lambda. Okay, and it is given by minus mc eta mu nu x dot mu x dot nu and the square root of it. Okay, so one has simply to replace L here, compute, and one finds the equations of motion. Alternatively, we can always vary directly the action and reobtain these equations by computing delta S with these boundary conditions. Okay, that all the worldlines start in x mu 0 and x mu 1. This means that if this is the physical trajectory x mu and the other ones are x mu plus delta x mu, then these variations x mu vanish at the boundary, which will be some values lambda 0 and lambda 1, at which x0 mu, sorry, x mu and lambda 0 or 1 takes the values 0 and 1. So let us vary directly this action. We have minus mc, which obviously remain constant. These variations do not act on lambda, so lambda stays there, and the only thing that you have to do is to treat this square root, and remember that taking variations is essentially taking derivatives, so this will be 1 over 2 times the square root of everything inside of the square root, which I don't write explicitly, and then the variation of eta mu nu, which is 0, so eta mu nu is there, and the variation of x dot mu, x dot nu. So let me just do this slowly. It will be this, okay, just as the derivative of the product plus x dot mu delta x dot nu. However, eta mu nu is symmetric, which means that I can interchange mu and nu, and I can also always relabel these contractions of indices and replace mu by nu and nu by mu. In the end, this means that this term and this term really are equal when they are multiplied by eta mu nu or contracted with eta mu nu. Let me write this whole thing then as 2 times eta mu nu, sorry, delta x dot mu x dot nu. Okay, these 2 and these 2 are going to cancel, And now I know that this variation is the variation of the derivative with respect to lambda of x mu. And as usual, since this delta does not act on this lambda is left invariant by delta, this derivative and delta commute, and we have delta x mu. So let me write this. This is minus mc integral d lambda, and then eta mu nu x dot nu divided by this square root and d lambda delta x mu. Then, as usual, we want something, the coefficient of delta x mu. And in order to get this, since delta x mu is affected by this derivative, we integrate by parts. We get minus mc, okay, a total derivative of eta mu nu x dot nu delta x mu divided by this square root plus mc the lambda, and then the derivative with respect to lambda of eta mu nu x dot nu divided by this square root, and everything multiplied or contracted with delta x mu. This integral can be performed immediately, and we just have to evaluate this is between lambda 0 and lambda 1. But since delta lambda 0, delta x mu at lambda 0 and lambda 1 vanishes, then this will vanish because of the boundary conditions. I haven't written explicitly the limits of integration, but it's clear that they were lambda 0 and lambda 1. So I am left with this piece, and okay, identifying the factor of delta x mu, I found that delta x mu, delta s delta x mu is just mc eta mu nu x dot nu divided by the square root, and with a derivative of time. Okay. And when this is 0, the x mu that satisfies this equation minimizes the action and is the classical equation of motion. Now, this is the result. It looks slightly different from the result that we got, or that we better guessed, okay, just based on arguments of symmetry, on the non-relativistic limit, and so on. But I'm going to show you that it is exactly the same. Of course, this factor mc that appears here, well, you can always add it. Furthermore, if you have eta mu nu, this eta mu nu can come out of the derivative, and you can always multiply these equations by, for instance, the alpha mu. Okay, so you have, and these are equivalent equations. You are just raising the index if you want, and this will be the derivative with respect to lambda of mc x dot alpha divided by this square root, okay, equal to 0. Then the main difference is that in the equation that we wrote that generalized the principle of inertia, or the law of inertia, is that instead of lambda we had the proper time. If lambda is the proper time, then this square root takes the value 1, and what we have here would be the ds up to this mc x dot alpha, where now this x dot is another derivative of the s. So really this is the same as mc x double dot alpha equal to 0, which is exactly what we got. This result is slightly more general because it tells us the form of the equations of motion for any parameter lambda instead of just for the proper time s. Now that we have derived the equations of motion, it is natural to study the conserved quantities that help us solve the equations of motion. These are associated to the invariances of the action via the first Noether theorem. So what are the invariances of this action? We said that the action is invariant under reparametrization. So if we change lambda by another parameter lambda prime, we are going to get an action of the same form, and the Pancary transformations. Let us start with the Pancary transformations because they are simpler to deal with. They have the form, the general form of Lorentz transformation, lambda, and space-time translation A mu. But what we need to apply the first Noether theorem are the infinitesimal forms of these transformations. Infinitesimal means close to the identity, close to the transformation that does nothing to the x mu's. So for the translations, close to the identity means that x mu is equal to x mu plus some small, very small parameter close to 0, because this is when x prime mu will be equal to x mu. Okay, so the deltas of these x mu's will be these infinitesimal parameters, and I indicate space-time infinitesimal space-time relations by this delta alpha. For the Lorentz transformations, things are slightly different. Okay, we have x mu equal to lambda mu nu x nu, and close to the identity means that this lambda is close to the identity indeed. So we really want to replace lambda mu nu by delta mu nu, the identity, plus something small that we call sigma mu nu. Then infinitesimal transformation, because this will be x prime mu equal to x mu plus sigma mu nu x nu, is this delta x mu equal to sigma mu nu x nu, and let me call these transformations delta sigma. We need a bit more information about these sigmas. In order to find it, we replace this expression for infinitesimal lambdas, for infinitesimal Lorentz transformations, in the condition that all Lorentz transformations have to satisfy, namely the preservation of the Minkowski metric. So if I replace this lambda mu nu here in this equation, I get delta mu rho plus sigma mu rho, eta mu nu, delta nu sigma plus sigma nu sigma. Okay, and I operate. First I use this eta to lower this index and becomes nu, and also this delta multiplied by eta will become eta rho nu. So I get eta rho nu, eta rho nu plus sigma nu rho, and now this multiplied by delta nu sigma plus sigma nu sigma. I multiply this delta first, I get, okay, delta doesn't raise or lower indices, just replaces indices, so nu is replaced by sigma, so I get eta rho sigma, and here nu is replaced by sigma, so I get plus sigma sigma rho. Then I multiply sigma by these terms, sigma times eta. Eta just lowers the index nu of sigma, so I get plus sigma rho sigma, and then sigma times sigma is of second order in something infinitesimal, and we just ignore it. And the condition is that all this is equal to eta rho sigma, which means that sigma rho plus sigma rho sigma is equal to 0. So this just tells me that sigma rho is minus sigma rho sigma. So sigma is antisymmetric. We can count how many independent parameters this matrix sigma has, because it is antisymmetric 4x4 matrix, and this has 6 independent components. Okay, this could be all the components in the diagonal must vanish because they have equal indices. So sigma 0 0, sigma 1 1, sigma 2 2 are 0 because I interchange them. I get the same but with a minus sign, so they must be 0. Then this one, I get this one, this 2, and finally this one, and all the rest are just the same but with a minus sign, so there are indeed 6. And remember that we said that there were 6 independent Lorentz transformations, 3 rotations and 3 Lorentz boosts. The rotations correspond to these 3 components, so this would be sigma 1 2, sigma 1 3, and sigma 2 3. These generate rotations. Spatial rotations, and these ones here, okay, these are these sigma 0 1, sigma 0 2, and sigma 0 3 are the Lorentz boosts. 3 and 3. It is interesting to make explicit the relation between these parameters sigma 1 2, sigma 1 3, sigma 2 3, and the parameters of the infinitesimal rotations that we wrote in the special relativistic case. Sorry, in the non-relativistic case. Remember that they had this form I, j, k, and the parameters were really these alpha j's, and then xk. Okay, the idea is that this combination, okay, which has 3 indices I and k, is going to be identified with sigma I k. So this is written in the form sigma I k x k. This is antisymmetric in I and k, and okay, sigma I k, so an index up and another index down, is minus sigma I k. Okay, how do I see this? Because this is just eta I mu sigma mu k, but this can only be different from 0 if mu is some index j, and eta ij is minus delta, so this is indeed this. Okay, so this is antisymmetric, and sigma ik is also antisymmetric in sigma ik. and this relates sigma k to the alpha j's. This relation can be inverted, but we will not do it here. This is just to show that these are exactly the same transformations, the same rotations that we wrote before, using different indices. Okay, of course the boosts are not there, these Lorentz boosts are not there in the non-relativistic case. Now, in order to write the conserved quantities just using the results of the first Noether theorem, we need the parameter independent form of the transformations. In order to write and handle these terms, I think it is completely necessary to introduce some notation that I have been trying to avoid. Okay, so the first thing is consider, this is a notational interlude, consider any tensor with two indices, for instance. There could be more, but they will not play any role. So these two indices could be two out of many other indices that we will not touch at all. Okay, we are going to define for this tensor two derived tensors. One of them is the tensor that one obtains symmetrizing the indices. This parenthesis here means symmetrization, and symmetrization means that I divide by 2 and I consider all the permutations of these indices with the plus sign. Okay, clearly this is equal to a mu. So it is symmetric. Okay, and it is derived from a mu, but it can also derive another tensor. Okay, these are not the same tensor. This is called Antisymmetrizer, these brackets, and the effect that it produces in a pair of tensors is that you add all the permutations of the indices, but affected by the index of the permutation. Okay, and clearly this is antisymmetric, so this is minus a mu. Interesting thing is that of course I can always decompose a mu nu in the sum of the symmetrized a mu and the antisymmetrized a mu nu. This is obvious because these terms here could cancel. Then the next thing is what happens if I have a tensor which is symmetric. Suppose that it's manifestly symmetric. So let me take b mu nu. Okay, or with the indices down, it doesn't really matter. Suppose that b mu nu is symmetric. This also means that with indices up, it is also symmetric. Okay, this you can try to prove it. It's very simple, but try to prove it to clarify, to check that your ideas are clear on this point. Okay, so let me contract b mu nu with a mu nu, which is general. Okay, then what happens is that this will be b mu nu using this decomposition, a mu nu plus b mu nu a mu nu. Now, whenever I contract something symmetric with something antisymmetric, as I have explained many times, gives you 0, because this will be equal to b nu mu. This will be equal to minus a nu mu, but now I can relabel nu and mu, so that they take the same form, but now affected by this sign. So this always vanishes. This means that only the symmetric part survives. So contracting with a symmetric tensor projects a general tensor in mu nu onto its symmetric part. If I have a tensor which is antisymmetric, Okay, I can write it like this. I will also write it in a different way. Then something similar happens, so I contract C mu nu with A mu nu, but now it is only the antisymmetric part that survives. Okay, if tensor is symmetric, I can say that its antisymmetric part vanishes. And I can also say that it is equal to its symmetric part. This is also obvious, but it is just a way to state with symbols that something is symmetric. And the same I can say about C. C, the symmetric part vanishes, and C is equal to its antisymmetric part. Okay, this is equivalent to saying that C mu nu is antisymmetric. Okay, so after this interlude, we can go back to our problem. Remember that we wanted to apply the first Noether theorem to this action of a relativistic particle here, using the fact that it is invariant under all the Pancary transformations, these ones. However, the first Noether theorem deals with the infinitesimal form of this transformation. So first of all, we derive these infinitesimal transformations, and now we have to write the parameter independent transformation. So remember that this delta x mu's, okay, the ones associated to translations have this form, but I need to write this as the parameter times something which is parameter independent. Okay, obviously this is just delta, because this is an identity, and now this object, okay, this is what I define as the parameter independent transformation of x mu. These parameter independent transformations are obviously labeled by a space-time index nu, which makes it a bit confusing. Instead of this capital A or something else, it is just nu. Okay, so this is why sometimes I write it in parentheses. It just means that it is really a label for these transformations. For the Lorentz transformations, this is a bit more complicated. Okay, this I can write in this form. But first of all, it is convenient to write deal with both indices up or down, because sigma mu nu is antisymmetric. We said this with indices up or down. Okay, so let me write everything with indexes up. So this is equivalent to this, because this eta lowers the index alpha, converts it into this nu. Okay, and still I have this index mu here, so I write sigma beta alpha eta beta mu. Okay, this is the same as delta beta mu. Sometimes I use this notation. And why is it the same? Because see, I can see this eta beta mu as the result of raising the index alpha in this. Okay, but this gives me delta. So raising an index and getting this delta is the same. So sometimes I just write okay, and I have this nu here, x nu. Now, because this is antisymmetric in beta and alpha, only the antisymmetric part of this tensor that has more indices, has indices mu and nu, but we don't care about them, we only care about beta and alpha. Only the antisymmetric part survives. Okay, this is going to be essentially the this part here. It will be the parameter independent transformation, but still one more piece of conventions. because this is antisymmetric, sigma 1 2 and sigma 2 1 are the same transformation, or they generate the same transformation. They are not independent. So we are, when we sum over all beta and all alpha, we sum over sigma 1 2, sigma 2 1, and so on. We repeat the same generators. In order not to do overcounting, typically 1 divides by 2, which means that you have to put a 2 here. And this is what we will denote by beta alpha. This is the parameter independent generator of the rotations. Okay, now we go to the formula. Remember that the conserved quantities have this form: x dot nu divided by this square root of eta x dot, and then the variation delta a x mu. This is the conserved quantity PA. Now for when A corresponds to a space-time translation, really this index is an index, for instance, nu, but nu has been used, so let me write P rho, and then we have eta mu x dot nu, and this delta rho mu. Delta rho mu times eta mu nu is eta rho mu x dot nu, which is basically what you expect. Wow, here I should have added a factor of mc. In fact, minus mc. Okay. Now, for rotations, you have your label capital A now is a pair of antisymmetric indices. For instance, this beta alpha, and now this is minus mc. Okay, this was divided by this square root. Minus mc eta mu nu x dot nu, and then this delta is this object here is 2 eta beta mu eta alpha, and now something different. Here we have nu, but we need something different, so I write rho, for instance, so it is x rho, and everything divided by this square root, so I get minus mc. This nu comes here and lowers this mu. Since eta beta mu and eta mu beta is the same, in order not to lower the index and put it here in the middle of the antisymmetrizer, I interchange mu and beta before, and then I get eta nu beta eta alpha rho, and then this is x nu x rho divided by this square root of eta x dot, and this is the quantity that okay, is usually called m alpha beta, really, instead of p alpha beta, and is the generalized angular momentum associated to all the Lorentz transformations. For each Lorentz transformation, okay, infinitesimal, which is associated to, well, I said beta alpha, which is associated to an antisymmetric pair of indices, say 1 2, you have this conserved quantity here, just the same as you have a linear component of the linear momentum. The component 0, which is nu with respect to the non-relativistic case, gives you the energy in this case. This expression for the angular momentum looks a bit horrible. You can just raise the indices, and if you raise the indices, okay, you will have minus mc eta nu beta eta alpha rho x dot nu x rho divided by this square root, but you see that this is contracted with this, so it gives you, and this is basically delta, and the same here, so this is equal to minus mc x dot beta x alpha divided by the square root, which is a bit simpler and maybe is a more common expression.